In Chapter 6, we'll be looking at mechanisms, and it is very important for you to learn how mechanisms work. It will allow you to rely on memorization of reactions a lot less as the semester progresses, and also in Chem 326 if you are continuing on to Organic 2. So it is very important for you to get the gist of how mechanisms work and get a good understanding of what is going on here. What we mean by mechanism is the arrow pushing, so you can see how electrons are moving. These usually involve polar reactions. Polar reactions involve ions as reactants, intermediates, and/or products. The negative charges are attracted to positive charges, so it's the opposite attract principle. Electron-rich species are attracted to electron-deficient species. So if it doesn't have electron density, it wants to go where there is electron density. If we look at methylene chloride, there's one carbon, the chlorine, and then the 3 H's here. We can draw the partial positive and the dipole moment, and this is a polar molecule. So this carbon is electrophilic. And we can see the electron mapping here. So this is where the blue means that it is electron deficient, and the red is where it is electron rich. Methyllithium has a carbon, but lithium is the one that's attached to it, and that's a positive ion, and the carbon then is partially negative. So we can see if we flopped the electron density around here. So this is the positive part of the molecule, and carbon is now rich. So this carbon is nucleophilic. So carbon can wear two hats. It can be negative or it can be positive. A nucleophile is an electron-rich species that can donate a pair of electrons. Nucleophiles tend to be Lewis bases because they can't donate that pair of electrons. A more polarizable nucleophile equals a stronger nucleophile. So if we can polarize the nucleophile, that makes it stronger. So a couple of nucleophiles that we see here is this carbon negative where the lithium is positive. Ethoxide is a negative charge. And then we have an example where the nucleophile is lone pairs, or it can be a pi bond. So all of these have electron density here. In a case where there is a formal negative charge, makes a stronger nucleophile because it is more polarizable. So we can send the electron density here because it's formally negatively charged. An electrophile is an electron deficient species that can accept a pair of electrons. So these are usually Lewis acids. Carbocations and partially positive atoms tend to be electrophilic. So this one here is just a partial positive. Here we have the formal positive. So that's a better electrophile. And you can see that there, this is an empty p orbital, so it's ready to react. This would be like your empty stomach and you wanting to eat something versus you just ate something, but you could eat something again. So this is the formal positive charge. It's ready to get filled. So here you want to label all of the nucleophilic and electrophilic sites on the following molecule. So nucleophilic sites come from inductive effects. So you have a positive ion here, or a positive association, which makes the carbon partially negative. You have a lone pair or a pi bond. So anytime we see those, that's going to be a site that is a nucleophile. So this includes the lone pair here, a nucleophilic site from the lone pairs. Here's another lone pair. Can be a nucleophilic site. This is another one. And then the pi bond here. Electrophiles form from inductive sites or an empty p orbital. We don't really have empty p orbitals here, but this is partially positive because this is partially negative. I missed one nucleophilic site, which is this one right here, because there's the formal negative charge. So this is kind of a tricky one here. This is actually an electrophilic site, even though this is positive. But if something were to get electrons here, those electrons would go up to take care of that positive charge there. So that one's kind of a tricky one. It's kind of an inductive one. So curved arrows are used to show how electrons move. as bonds are breaking and or forming. We used them already in acid-base reactions. Remember, we went fishing with our fish hook to grab a proton, and those electrons moved here. So these electrons went to grab this hydrogen that formed a new bond, and those electrons went on to the A. So now we have BH and then A minus. And there's 4 ways that we can move electrons in polar reactions. The first is a nucleophilic attack. This is in no particular order. The second is a loss of leaving group. Third is proton transfers. And this is the type that we've seen already with acid-base reactions. And the fourth, which is the trickiest one, probably is rearrangements. So in a nucleophilic attack, pi bonds can also act as nucleophiles. Pi bond from this benzene ring can attack sulfur. So sulfur, if we draw dipoles, it has 3 partially negative oxygens here. That makes this very electrophilic. So this is my nucleophile. This is my electrophile. So we're going to get a nucleophilic attack on the electrophile. And then one of these electrons will go on to the oxygen. So I formed a new bond with sulfur. And when I did that, I took electrons out of this bond. So one of these carbons will become positive because I took electrons out. So my other 2 oxygens stay the same, and the oxygen that electrons went up onto becomes negative. So it's got 3 lone pairs of oxygens now. So that is a nucleophilic attack. So here this pi bond is going to act as our nucleophile, and this is kind of our electrophile. And that is partially positive, this is partially negative. So this will grab the hydrogen and attack there. Well, that goes on to there. This one could be a nucleophilic attack, or it could be a proton transfer, but this is just to demonstrate that pi bonds can attack here. So I formed a new bond with hydrogen because these pi bonds came out here, and that becomes positive, and we have Cl minus. If you noticed here, only one of the carbon atoms from the pi bond uses the pair of electrons to attack the electrophile. So that one of the carbons from the pi bonds adds here. The other one gets a cation or a positive charge there because we took electrons out of there. Only one of the carbons got the hydrogen, not both of them. So that's nucleophilic attack. The next is loss of a leaving group. This involves a heterolytic bond cleavage where an atom or group takes the electron pair. In English, we have a leaving group, and that's going to get lost. So the electrons from this bond here can go on to the bromine. So we get this here plus the bromine. So when these electrons came out and went onto the bromine, this left this carbon deficient. So now it has positively charged, or becomes a carbocation, and that bromine got an extra pair of electrons. So before it had 3, now it has 4. So this is loss of a leaving group. Sometimes we can use more than one curved arrow to show how the leaving group leaves. So our leaving group here will be the chlorine. So Lg is for leaving group. So this one's going to involve a couple of arrows. There should be a double bond on this nitrogen so you can fix your slide. So it's common for more than one arrow to be involved. Like I said, this negative charge from the oxygen can come in here to form a double bond with the nitrogen, which will make too many bonds to nitrogen. So one of these electron lone pairs can come down to this bond, which again makes too many bonds to this carbon. So this will come here. And then there's too many bonds to this carbon, so the chlorine will leave. So you can see all of the new bonds that are formed here. We'll just follow the arrows, and then we get plus Cl minus. A proton transfer, which is from chapter 3, is just usually 2 arrows where a proton gets moved around. So in this case, we have the oxygen lone pair can grab the hydrogen. These go on to here. And then we get this oxonium. Deprotonation is just the reverse of the arrow. So this water can grab the hydrogen and give the electrons back. And then notice that the charge stays the same. So we had a positive charge on this side, and now the positive charge is here, positive here, and it's positive here. So those stay balanced. So sometimes multiple arrows can be necessary to show complete electron flow when an electron is exchanged. So I'm going to do a proton transfer here. This OH minus is going to grab this hydrogen. These electrons come down here, which makes too many bonds to carbon, so those electrons get pushed up. So there's only 2 hydrogens here now, and I formed a double bond here. This now has that many, and then we have HOH over here, or water. You could also think of the hydrogen going here, and the electrons going on to this carbon. And you could get that structure, and then this is in resonance with that one. So if you drew these electrons into here and on there, those are in resonance together. So in rearrangements, carbocations can be stabilized by neighboring groups through slight orbital overlapping called hyperconjugation. This methyl group here stabilizes the carbocation by sending electron density through the bond. So it can donate electron density into the p orbital. If you increase the substitution, that increases the stability of a carbocation due to the increasing number of adjacent sigma bonds aligned with the empty p orbital. So what that means is this is a methyl carbocation. It's not very stable because it only has hydrogens there to support that positive charge. If you add a carbon group here, this is a primary carbocation, and that has the support of 1 carbon. So this has more electron density, so it can bring more electron density into that carbon to support the positive charge. Here you have secondary, so there's 2 carbons now supporting that charge, which is better than 1, which is better than 0, and this is tertiary. So this is one of the more stable carbocations. So stability increases that way. So carbon doesn't love to be positive, but if it has to be, it would rather have its friends here supporting and sending its electron density in to support that positive charge. So there's 2 types of carbocation rearrangements that are common. There's a 1,2 hydride shift. So what happens there is this hydrogen shifts over to this carbon. So this whole group moves over. That is a secondary carbocation. And again, the carbocation is a carbon that's bonded to 2 other carbons. So that one's relatively stable. But if we shift the hydride over to here, it moves here. And when I move that electron pair over, that positive charge now goes onto this carbon. And this is a tertiary carbocation, which is more stable than the secondary. You can also have a methide shift, methide or alkyl. So this whole group, again, we had the same secondary carbocation, but now there's a methyl group here. That whole methyl group can go onto this carbon. So I've now moved that to here. When we move this methyl group here, the positive charge went from being on this carbon to over here because I took that electron density out of there. So we have, again, a tertiary carbocation. That's more stable. So shifts can only occur from an adjacent carbon, so we can't move from carbons far away. And it only occurs if a more stable carbocation results. So if we formed a tertiary carbocation, it would not shift backwards to make a secondary because that's less stable. Or if you had a secondary carbocation, it would not shift to form another secondary carbocation. So multi-step reactions usually combine multiple patterns. So the reaction that we're looking at here combines all 4 of the types of arrows. So in this first one, we have an oxygen grabbing a proton. So this one is a proton transfer. This can also be written as a plus minus H, just to show that you're adding a proton, and then later if you remove a proton, that's the minus proton, or you can call it a PT for proton transfer. So once this oxygen grabs the hydrogen, this is now a water which can leave. So this is a leaving group, and this type of arrow is a loss of leaving group. So this is my leaving group. Here we have an alkyl shift or a methyl shift. So this is a carbocation rearrangement. So that moved over here. We had a secondary carbocation, and now there's a tertiary. And then this here is bromine with a negative charge, and there's a positive charge here. So this is my nucleophile. This is an electrophile. We have a nucleophilic attack. In some reactions, we have arrows that will happen at the same time. So here we have a nucleophile and an electrophile, and that's due to the partial positive, partial negative. So we have a nucleophilic attack followed by loss of leaving group. So when we're drawing arrows, the curved arrow will start on a pair of electrons, which is a shared pair in a bond or a lone pair. So you can see on a lone pair, these electrons are going to form a bond here, and that one is breaking the bond, so that's leaving. So this is the new bond that is formed. And then we have plus Cl minus. The second arrow here is drawn incorrectly, and that is because we want to show the electrons going from here. So that's one part of it that is wrong. So this attack is fine, but this arrow should be between the bond. So it should come from here, not there. The head of the curved arrow shows either forming a bond or formation of a lone pair. So here is forming a bond, and then that's forming the lone pair. So we had the same product as before. So we're forming that lone pair, and the head of a curved arrow can never show carbon forming more than 4 bonds. So we can't have an electron attacking here if this carbon already has 4 bonds. But if we have the oxygen lone pair attacking here and this leaving, that's not violating the rule. Any curved arrow drawn should describe one of the 4 patterns discussed. So we either are drawing a nucleophilic attack or a loss of a leaving group. Again, this is the same product that we keep seeing. But this arrow here is not reasonable. It violates the octet rule. Is not one of the patterns. That's an sp3 carbon with no leaving groups. So you would be forming too many bonds to that carbon. This is an sp3 carbon with no leaving group. This is not an electrophile. So when you encounter a carbocation, you have to consider if a rearrangement in either hydride or an alkyl shift could result in a more stable cation. So you look at the hydrogen atoms and or methyl groups on neighboring carbons and then determine if shifting one of those groups forms a more stable carbocation. So right here I have a secondary carbocation. So I look at this hydrogen here. So let's say I was to move this hydrogen over to here. So if I did that, that hydrogen comes here, my positive charge moves here, and I have a secondary carbocation again. It doesn't really help because it's not more stable. If I have a hydrogen here, which I do, and if I move that to that same carbon, the hydrogen moves here, my carbocation is here. This is a tertiary carbocation, which is more stable. So if it doesn't make sense to form a carbocation, then it won't happen. But if it makes it more stable, then it will happen. Tertiary carbocations will typically not rearrange unless there's a resonance stabilized cation that is formed. So this is a tertiary carbocation. This one will not rearrange. If I had a similar structure, carbocation is here, and I have a hydrogen here, this is tertiary. If this goes here onto that carbon, this hydrogen goes here, and now it looks like I have another tertiary carbocation, but this one is actually stabilized by resonance. So that one will shift, this one will not. So you can practice drawing arrows here, or you can watch me do it. The first thing that can happen is when you're given a whole mechanism and you just have to draw the arrows, you kind of want to look at what's going on next to see what's different here, and have an OH here. So this is my nucleophile. This is the electrophile. Nucleophile will attack the electrophile. That would make 5 bonds, so I'm going to put electrons up here. So this is a nucleophilic attack. So this is the new bond that formed here. So I'm just drawing this so you can see where it went. And then we have 2 electrons that came from there and this minus charge. In the next arrow, if we look, we have 2 lone pairs. There's a double bond that reformed, and then we have this here. In this case, this part is the leaving group. So these arrows or electrons will come down to reform the double bond. This will go on to here. So we get lone pair on that electron. This bond was formed, and we have that. So this arrow was the loss of leaving group. And we said that sometimes it can take multiple arrows to get the leaving group to leave. And in the last one here, what we see is the O minus here has grabbed a proton from the OH. So this one is a proton transfer, or a plus minus H, or a PT. So we have this lone pair will grab this hydrogen, and those will go on to the oxygen. Then we have the lone pair, this minus charge, and this H that is new here. And that's the proton transfer. We'll see this in chapter 7, 8, and etc.